So hi everyone, I'm Ricky Zhang.
Hi, my name is Suresh Devalapalli. We are from a company called Gaussian Solutions. In collaboration with Tasker Center at University of Washington, we just finished mapping pedestrian network across the entire state of Washington, and that's what we're going to talk about and how we achieved it. But I think before we get into the details, we should first talk about who cares about sidewalks and why does it matter. Well, yeah, we can help your game with this for sure. So the most people that we work with most is transit agencies, and they would like to do the first and last mile connectivity analysis and improve access across to the transit network, to the transit stops and transit corridors. Second, we have city planners. Obviously, they would like to plan the cities with more connected multimodal transportation and also want to identify the infrastructure gaps. So that's what this data is also used for. We have developers and architects who want to develop with accessibility and walkability in mind. Then we have equity and justice organizations, which are looking at underfunded neighborhoods and how to bring that up to mark. And yesterday, Clifford talked about safe routes to school. That's one of the biggest use cases as well. So ensuring student gets to school safely and where to improve the sidewalks to make that happen. And finally, academics who are interested in studying about social health and environmental studies also need this data. At a glance, Washington State is pretty huge, 184,000 square kilometers. And when we finished mapping, it was 36,000 kilometers of sidewalk, 6,700 kilometers of crosswalks, and about 133,000 intersections that were mapped. So first, let's look at, can we do it manually? Of course, the answer is yes, but what does it take? We did bring out some mappers and initially did an estimate, and we characterized the state as urban, suburban, and rural. In urban areas, we take about to the quality that we are looking for, it takes about 10 hours per square kilometer. In the suburban area, it's about 7 hours, and in the rural, about 45 minutes-ish. So if you put all those things together, even though state is like 184,000 square kilometers, only about 7,600 square kilometers is populated. Even with that, we're still looking at 15 human years. Obviously, that's not acceptable. And hence, we started with our project, which is let machines do work, and Ricky will talk more about that.
Thank you, Suresh. So here is the overview of our pipeline. We built this end-to-end pipeline, which is called the Pedestrian Routing Infrastructure and Street Mapping AI, or the PRISM AI. So as you can see here on this image, there's two parts to our system. The part on the left that's being highlighted right now, it's our fully automated end-to-end AI power pipeline that taking multiple sources of orthogonal data sources, which include the aerial imagery and the existing street map imagery or other available information. It could be the DEM data or any others. And then it will output is a connected routable pedestrian pathway graph at the scale of the states. And we also have a human in the loop interactive data vetting and visualization too, which we also talk about later. So when we look at any machine learning pipeline, the first step is to get the data. And unfortunately, all the current data sets that's available to the public mainly focus on the buildings or streets, automobile roads. They don't really have the necessary class that's annotated to accurately understand or describe the pedestrian environment. So the first step of our pipeline is to build our own data set that targets the pedestrian environment specifically. We built this data set called the annotation for the pedestrian environment, or the APE data set. So what this data set contains is the annotation of the connected pedestrian pathway graphs. And then for each of the graphs, we also provide the rasterization of the graph for computer vision or any other vision-based algorithms. In addition to that, we also have 3 other co-register exactly aligned features that can be used alongside the samples for the learning. And with the aim to reduce the learning bias in the data set, we built this diverse data set that span across 10,000 kilometers of land area, including the entire Washington state and also several other North American and South American cities. And now that we have the data, we can look at the actual modeling part. So at the core of our system is the system we call the Pedestrian Path Network Graph Inference Method, or the PROPHET, which will take in the data and then do the inference in 3 separate steps. And then we can look at the first step, which is what we call the seeding step. Next one. And this is another standalone tool that we built called Pedestrian. What it does is it looks at the existing street infrastructure or any available automobile roads, and then make a hypothesis of the sidewalk locations, and then also the crosswalk locations, as well as the curb interfaces that connect the sidewalks and the crossings. What comes out of the Pedestrian it's a routable and connected graph, but sometimes it's not that accurate or over-optimistic. So that's why we need to use some other information to refine and improve the graph. That's why we need to move on to the second step, which is the prediction step. So here is where we use AI and specifically computer vision to help us understand what's actually in the pedestrian environment, as can be seen from the computer vision part. So we built this state-of-the-art multi-input segmentation network that takes in multiple input. What I'm showing here is one of them being the aerial imagery, and then the second input being the rasterized street network tiles. So we use this hierarchy learning schema to kind of fuse the information, learn from the 2 different branches, and then use them together to generate the pixel-wise prediction for the image. And through our experiments, we found that using multiple sources gives us the best result compared to using only one sources. This one. And now we have a seeding graph. We have some information we learned from our computer vision model. In the next step, we can combine them together into a more accurate pathway graph. So just as an example here, you see in this example, the first image is what we got from our Pedestrian tool. You see it has the basic geometry, topology, locations of the pathways, but it's not in the best location, as it's in the middle of the road. And then we move on to the second one, which is our optimized pathway graph that we use the information we learned from our computer vision models to refine the first graph. And then we're showing this comparison in the last one, where you can see our optimized output is very close to what's vetted and mapped by the human mappers. And besides this, so that was the end of our fully automated pipeline, which just takes in data and then can generate the output without human intervention at a very large scale. And there are some issues. That's why we also have this human-in-the-loop interactive tool for data vetting and visualization. So the core idea is that while our machine learning model output the prediction graph, we also output some of the confidence that tell us how good this area is, or is there some issue that will flag it for further human vetting. So once we know where those potential issues are, we can have human mappers just focus on those potentially problematic areas instead of letting the mappers going through each individual intersection or sidewalks for vetting. And on the other hand, once we have this vetted data, we have better data now, we can feed it back to our AI model for training. So we have like a better model, more generalizable, or more accurate in the next iteration, and this just go on. And now we end up the pipeline. We obtain our outcome. So this is just a visualization of what's output by our framework. It's fully connected, routable, contains different elements, including sidewalk crossing, marked crossing, unmarked crossing, other footways, and also the curb nodes to show the connection point. And then most importantly, we generated our data in a standardized format per the open sidewalk schema, which is a extension that we built on top of the OSM schema. So it's fully compatible with the OSM schema can go directly back to OSM and directly used by other downstream applications or loaded into the Rapid editor. And here is other examples of data that we generated. We generated the entire Washington state, as we mentioned. In addition to that, we have 4 entire counties in 2 different states, total of about 30,000 square kilometers of land area that generated with our pipeline. And here's the QR code you can scan to view our data. And with this, I'll hand it back to Suresh.
Yeah, so we also did a comparison of what data is currently available on OSM and what we currently have. And this is just 3 examples of Wenatchee is in central Washington. As you can see, there's hardly any data on OSM, but we have really good data over there. Same with Yakima and Marysville. We did build a visualization tool. So if you go to that QR code over there, by default, you'll see OSM data, and there's a button. If you click on it, you'll see our data overlaid on top of it, and you can see the difference. And the reason we built it is we want the community to start taking this data and pushing it. So I'll come to the call to action in a second. We really thank the community because most of our workflows are based on the tools developed by this community. So really thank you for that. If anyone is interested in this, come talk to us. And this shows like the path we take through the whole pipeline to get to the output. So how can we engage? As I said, the data is open. Like you can easily see it, comment on it. We have enabled commenting on it. So if there is, it's still possible once in a while that we made a mistake or something. So please. And as I said, our data is OSM compatible. We can make the change sets and all that, but we do need some help from the community to get it into the OSM. And if anyone is interested in like building their own workflows and such, depending based on the OSM stack, we have done that. So please come and talk to us. And most importantly, if you are in Washington, or if you want to do some work in Washington State, in fact, Tasker Center has a grant open now. It can be up to 10,000 or 100,000, depending on the idea. It has to use the data set that we have generated, and it has to be impactful in the state of Washington. But if anyone has ideas, please go and apply to SCLEOs. And that's our talk, and that URL will take you to, our QR code will take you to the visualization. Thank you.
Thanks so much, both, for the presentation. It looks like we have a couple minutes for questions. Does anyone have any questions? See one over there?
Yeah, thanks for the great presentation. You had a slide where you showed the different data sets for the different municipalities that you created the data for. Were any of them more challenging than the other, just based on their built environment?
It so happens that cities are easier, but the rural areas are much more heterogeneous, so it gets difficult to do there. Do you have any other comments on that? Keto? No. Yeah.
Yeah, of course.
Have you done any analysis of what makes a sidewalk pleasant to walk around? So like this one has trees, this one is not next to a 50-mile-an-hour road or anything like that.
To walk around, we didn't do it, but Sam, who is right there, that's most of his access map has lots of variables that you can plug in. Like you can choose a route that's next to points of interest and something like that. They are the downstream application of our data. So it's one of the use cases, yes. Sam, you have a poster, right? Yeah.
Cool. OK, thank you so much.
Yeah. Thank you, folks.
Sure.